Alright, physics. When we left off, we were talking about circuit electricity. We talked about the different pieces to a circuit, what you need to make one. And next thing I want to do, next thing I kind of want to look at and focus on are these guys down here, these circuit symbols, right? So we can draw out basically a simplified circuit or what it might look like. So what I want to talk about are basically these circuit symbols and how they relate to what we call series or parallel circuits, right? Because there is a difference between how circuits are put together and kind of how they work. So I'm going to take these three principles from before, needing a battery, a wire, and a resistor, and we're going to draw them out. I'm going to draw them out. And I'm going to keep this kind of in the top left here for a second. Because something occurs to me. Like the tiniest bit too big up there. That'll do. Okay. So we have those symbols over there. And using those symbols, I'm going to create the simplest circuit possible. Right? Something that has a battery, a wire, and a resistor. Right, so here it is. Charges flow like this. They flow around. They get charge, or they get voltage from the battery. They travel around. They use it to go through the resistor, and then they travel back to the battery, rinse and repeat. All right. Now, this is the simplest circuit because, again, we have our voltage source, we have our wire, and we have our resistor. Right. Now what I'm going to do is make it exactly one piece more complicated, but I'm going to do it in the context of having what we call series and parallel circuits. Right, so I'm going to take those pieces, I'm going to add one more. So I'm going to have my battery connected to a resistor and another resistor, and then we'll just connect right back to the battery. Alright, so let's call this resistor 1, I'll call this resistor 2, hello, call this resistor 2, let's call this voltage V. Alright, so this picture where there is exactly one loop, right, this is called a series circuit. Characteristics of a series circuit. One loop for charges to travel within, right? So there's only the one option. They have to go through R1, then through R2, and then back through V. Right? Another characteristic of a series circuit, because there is one loop, the current is the same throughout. Right, so there's only one current, there's only one speed that charges can travel at because there's only one pathway. Right. The last piece that I'll talk about here is removing one piece I'll come back to those things in a second. Breaks the circuit. Right, so if I remove any one of those, if I remove resistor 1, then there's just a gap. If I literally remove this, I'm trying to be deliberate. Remove, not replace. If I remove that piece, circuit stops working because there's no more closed loop. Alright. Now I'm going to take this. I'm going to take these same pieces. I'm going to take a voltage source and two resistors. I'm going to connect them again and connect them differently. So I'll do this. I'll do this. Right? Again, this is still our... Oh, that's annoying. There we go. This is still R1. This is still R2. Alright. This time, I've connected them differently. I've connected them in what... That's not how you spell parallel. Words are hard, guys. Parallel circuit. Alright. Key characteristics of a parallel circuit. Multiple loops. Right, for charges traveling. Current is different in each loop. Charges will try to find the path of least resistance. You should be kind of familiar with that phrase just from other stuff, maybe other sciences. Generally speaking, the current will be faster through the smaller resistor and faster through the smaller resistor, slower through the larger resistor. Sorry. And here, removing one piece. I should be a little more specific here. Removing one resistor. So removing one resistor does not break the circuit. Right? If I remove R2, there's still a loop. There is still a full loop that charge can travel through. Oh goodness. There we go. So there's still a full loop the charge can travel through, even if I remove R2 or if I remove R1, right? One key thing about parallel circuits, the path of least resistance is not always the shortest literal path that's drawn. R2 might have a smaller resistance than R1, so more charges would prefer to take the R2 path, even though visually it's the longer path, specifically because it's the path of least resistance. Right. Now, what I'm going to do here is I'm going to look at these properties with respect to the circuit. Right. This says that the current I is equal at I1, I2, I3, and so on, right? So when we number things here, we're talking about specifically through that resistor, right? I know there are 3 here and I only have 2 in my drawing, but it still applies. The current through R1 is the same as the current through R2, and we said that. I had said that already here. And the reason for that, the reason for those being the same, is because those resistors, because there's only one loop, right? So there's no traffic jam for charges, right? Just because one resistor is bigger than another doesn't mean it slows it down a ton in that one spot, and then they're allowed to go faster in the next spot. They always have to go the same speed because there's no traffic jams for charges because charges are charged. They want to be a certain distance away from each other all the time because they will constantly repel each other. It's not the case with cars. Right? Cars you can traffic jam because you can get as close as you want to the next car in front of you until you hit it, and then I guess you can't get any closer. Wouldn't recommend doing that. Alright, the next property of series circuits here, they say V equals V1 plus V2 plus V3 and so on. So this total voltage V is going to partially get used here at R1, partially get used here at R2, and then will return with no excess voltage. Remember that this voltage source gives charges extra voltage. It's not the charges have zero energy and they just, right? They have a baseline amount of energy and it's just kicked up by the voltage source. So that extra energy will get used a little bit by R1 and then by R2. Right. The last part, this Req, this is the equivalent resistance, or the total resistance, and it's equal to R1 plus R2 plus R3. So as I add more pieces to this, the total resistance goes up, which should kind of make sense. The more roadblocks, the more resistors you put in the path, the more resistance overall that there will be. So you simply just add them up together like normal. If R1 was 2 and R2 was also 2, then this would have a... well, let me do this. This is... let's say that R1 is 2 ohms. And R2 is 3 ohms, right? So the equivalent resistance here would be 5 ohms, because that's 2 plus 3. So this has an equivalent resistance of 5 ohms. It's fairly difficult to get through-ish, right? Now, it'll move. It's just taking a second. There we go. Now if we look at the parallel circuit properties, this says that the current is equal to I1 plus I2 plus I3, right? What that means is that the total current has to be equal to how many charges go through pathway 1 plus how many charges go through pathway 2. If you look at this and you think about it, all of the charges have to go around this first bend, right? Some of them will go this way, and some of them will go this way. But eventually, down here, they have to meet back up. And it's going to be the same number of charges as before. Right. Now again, this ties back into more charges will take the path of least resistance. Fewer charges will take the path that has more resistance. But they're not all only going to take one path, because they want to keep that spacing. They want to be as far apart from each other as possible. Right. The second piece here, in a parallel circuit, the total voltage is the voltage in loop 1 is equal to the voltage in loop 2 is equal to the voltage in loop 3, and so on. The reason for that, again, remember, the voltage source gives the charges excess energy. That excess energy is used to go through this loop, right? If this is the only resistor we have to go through, then this will use all of its energy to go through that. Alternatively, if this is the only resistor to go through, it will use all its energy to go through that, right? Let's pretend again that R1 has a resistance of 2 ohms and R2 has a resistance of 3 ohms. This equivalent resistance for a parallel circuit is a little funny. It goes like this: 1 over the equivalent resistance equals 1 over 2 ohms plus 1 over 3 ohms. I beg of you to please do not say that this equals 1 over 5 ohms. Please don't do it. Alright, find a common denominator and do the math that way. So this will be 3 over 6 plus 2 over 6. Well, that's 5 over 6, right? That's 1 over the equivalent resistance equals 5 over 6. You can cross multiply and divide. I would just recommend flipping both sides. If I flip both sides, right? So 5 over 6 equals 1 over Req. That means that 6 over 5 ohms equals Req. Right? That's the equivalent resistance. I want you to notice, this is smaller. This is 1 and 1/5. This is 1.2. Like if I was going to actually do this math. Oh. Okay. So, this is 1.2 ohms. That's smaller than either of the resistors there. That is a common property of parallel circuits. Generally, here, I guess I can add this to both of them. Right, for a series circuit, adding resistors increases the equivalent resistance. If I add resistors in series, it increases the equivalent resistance. Adding resistors in parallel decreases equivalent resistance, right? It makes it easier because it creates more pathways. Adding resistors in parallel creates more pathways, means that charges have more choices, means they can spread out more. That makes it easier for them to travel, right? Now, again, that was just baseline of, here is a visualization of what you will see. Here are the circuit equations I guess, if you want to call it circuit properties, right? Properties of series and parallel circuits. Um, Next class, next video, next little mini thing will be kind of wrapping up with these last three equations and just explaining what a voltmeter and what an ammeter do. Won't take a terribly long amount of time, and then we'll kind of be done with electricity. I'll give a little another little like electricity, well, probably an electricity test just on like literally everything, because we've done electricity. The first part that we did was static electricity, then I explained the next part of circuits, talked a little bit about the symbols here. Once we finish this whole thing, I'll be able to test you on basically all of electricity, which isn't like a ton, right? So here's our little electricity corner, right? Compared to the rest of the year that we've done, right? All up here. So it's comparatively less. I realize I've been going on and on a bit here, so I will wrap this up. There are going to be questions on this, kind of like usual, right? It'll be on diagrams and working with these equations, working with the properties. You already have a quiz scheduled, and there'll be a test. It probably won't be like officially until 5th marking period. I don't think it'll be until then, but if I can sneak it in, I will. I don't think I'm going to. There will be a lab that I want to do with circuits. It might end up being a simulation for everybody. There's definitely a simulation I can do for fully remote students, but depending on what I can get to work in class, we'll see. In any case, I will see you in the next video or in the next class. If you have questions, please email. Otherwise, until next time, take care, kids.